Right, okay, so I'm going to go through principle of superposition of waves and formation of stationary waves today. Sometimes called standing waves, we call them stationary waves. And they are waves that are produced by the superposition of two waves with the same frequency and amplitude travelling in opposite directions. Normally, it's a wave and its reflection to give us those conditions. And the key thing about stationary waves is unlike progressive or travelling waves where the energy goes from one place to another, a stationary wave is essentially a store of energy. There is no energy transferred in a stationary wave because it's reflecting back on itself, or it is just two waves going in the opposite directions. Now, you have to have an understanding of how stationary waves are formed, so like a graphical understanding of this, which I am going to attempt to demonstrate on this little. You might think, why didn't you get a ruler? But there you go. Think that all you like. So I'm going to attempt to demonstrate that. So I'm going to show you two waves. I'm going to draw two waves going in opposite directions. So the first wave is going to be this orangey sort of colour, and it's going to be like this, right? And this wave is travelling in this direction. The other wave is going to be this greeny wave, like that. And that wave is travelling that direction, okay? So what I'm going to do first, just to help me not get muddled up with it, is I'm going to draw the progression of the orange wave. So the idea is the orange wave is going to start here and it's going to end up kind of like over there. It's moving this direction. Now, obviously you could draw this at like any point on the wave. I could, an infinitesimally large number of waves that I could draw as I kind of trace each path and move it over. But I'm just going to kind of skip ahead a bit and move it on. So it starts kind of halfway between one of these lines at each point. So I'm going to draw all the orange waves and then I'm going to draw all the green waves, and we can see what happens as they overlap. So this orange wave starts here, and then it's going to be like this after a quarter of a cycle. After another quarter of a cycle, it's going to be kind of back to between the lines like this. Another quarter of a cycle, it's going to be starting here and ending there, and then back between the lines for the last one here. And I could keep going, but we'll see what happens enough with these 5 waves I've drawn. So the next one, I'm going to draw the green waves. Now the orange wave's going, you can see it's traveling that way. So this is like a snapshot after bits of time. The green wave is going to go this way. So after a little while, it's going to be starting, quarter of a cycle, it's going to be starting here. And they are going to overlap straight away there. Well, it makes sense, they're touching there anyway. Then after another quarter cycle, it's going to be here. And then after another quarter of a cycle, it's going to be here. Oh, and this is when they're beautifully on top of each other. And then another quarter of a cycle, and it's going to be like that. Now, you can kind of already see what's going to happen with these waves when they overlap like this. You're going to get points like here where these two waves are meeting in phase. That's a peak meeting a peak. So that's going to be a superposition creating a wave of double the amplitude of the original wave. So these two joined together is going to be like that, mega wave. Now, here though, that's peak meeting trough. And another peak meeting a trough. So these waves are actually going to flatten out like that. So you're going to get a peak wave here and then a flat. And then here again, you can see these have lined up again. So it's going to be mega wave like this. And then here again, I mean, I'm not drawing it very well, but these in theory are going to be the flattening out again. Now, some points are always going to end up cancelling out. So along this line here, we're always going to get cancelling out. That's never going to move. Doesn't move there because it's, even though they're adding up to make the kind of mega wave there, at this point it still remains in equilibrium because they were in equilibrium here anyway, both of them. And so when they're in equilibrium, so I mean equilibrium would be this for all the waves. That would be equilibrium. If there was no wave travelling through the string, that's what the string would be like, or the air or the electromagnetic field or whatever it is. And then here they're 0. Here it's also 0 displacement from the equilibrium. Here, which is supposed to be in the centre, 0 displacement, and back here. So there are some points on this, and if I were to draw it better, it'd probably look better, but there we go, where it's always 0 displacement. Then there are some points where sometimes it's maximum, sometimes it's 0, sometimes it's minimum, right? And then obviously everything in between, right? So this wave was always moving in this direction. and this wave was always moving in this direction. So these two waves moving in opposite directions have created this kind of like pattern as they cross through each other of sometimes points never moving, sometimes points always moving. Now, this then, as I've no doubt you've seen, can be represented on a string in the formation of these sort of like stationary waves on a string, and that's one of the required practicals to investigate this. Now, straight up, you get an equation for these stationary waves on a string. You get the equation for the frequency of the first harmonic is equal to 1 over 2L, where L is the length of the string, T is the tension in the string, and mu is the mass per unit length of the string. The tension and the mass per unit length go as part of like what would the speed of the wave be, but we're not too worried about that. We get given this equation. Now, you have to have different frequencies to find this, right? So this frequency is this frequency here. Now we can see for this one, the way I've drawn it like this, obviously the rope would never be in both positions at once, the string or the microwaves or the sound waves, because this can be created with microwaves or sound waves as well, would be either up there, down there, up there, down there at any particular point. Now, for this one, what's happening is you've set up the frequency so that the wavelength of this wave, the wavelength, is exactly twice the length of the string. I quite often get that wrong, but that's half a wavelength we see there. So if we doubled the length of the string, we'd expect to see 2 times the wavelength, right? And then it's kind of a case of analysing wave speed as frequency times wavelength to get this kind of equation with the idea of what the speed of the wave is, but it doesn't matter because we get given it. Then what's happened if we double the frequency, now we get the wavelength is equal to the length of the string. So if we've got this wavelength is now the length of the string, so we've halved the wavelength, we must double the frequency. So for this frequency, we use this same equation here, but now the frequency is twice this, which was just going to be 1 over L square root of T over mu, or sometimes, just to make it clear, put twice all of that, right? So twice the same frequency. And on this one, you can more clearly see the nodes. I mean, there was a node on this one. If it's a fixed end, it's always going to have a node on it because it can't move. If it's an open end, it's always going to be an antinode. But here we've got a fixed end here, but in the middle here we also have a node. So this is one of the places from over here where no matter what happened, it was always cancelling out to be equilibrium, or they were both at equilibrium anyway. And then this here is the antinode where it goes to the maximum. So this would be kind of like this bit in the middle. So it goes sometimes at the maximum, sometimes at the minimum. And it basically just happens so fast that your eyes can't really process it. And what it really looks like is kind of just like a blurry packet. But like I say, I'm sure you've seen it. If you haven't, look up a video of it because they're everywhere. So for the third harmonic then, if this is the length of the string, the wavelength, right? The wavelength of this one is now 2/3 of the length of the string. So if the wavelength has been reduced by a third, right? So because our original wavelength here was 2 times the length of the string, now our wavelength is 2/3 of it, so it's a third. That means the frequency must be multiplied by a third. So our new frequency is going to be a third times this, 1 over 2L square root T over tension over the mass per unit length. And then finally for this one, if this is the length of the string here, now you can see the wavelength is a half times the length of the string, because this is one wavelength, which is half the length of the string. And so if our wavelength, from our original one here, the wavelength was twice the length of the string, now it's a half. So the wavelength has fallen by a quarter. So we're going to multiply the frequency by a 4. So it's going to be 4 times 1 over 2L square root of T over mass per unit length, tension over mass per unit length. This equation obviously only applies for a string where there's tension, but the same principle kind of applies for microwaves and sound waves, and they might ask you questions on that because that is on the specification. There are other terms for this, but these are all the terms that AQA want you to use. And obviously, just to be crystal clear, we use the wave speed is equal to frequency times the wavelength to make our assumptions that if we're going to reduce the wavelength, we must increase the frequency, and they're directly proportional. That is it. Let me know if you want any further detail on that one. Thanks.